Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Scanning Near Field Optical Microscopy from the paper Characterization of Materials 1. So students, let us see what we are going to learn in this module. In this module, scanning near field optical microscopy, that is SNOM, is described. Then the evanescent waves are described and the optical resolution is discussed in this module. The various modes of operation, feedback mechanisms, and contrast techniques of scanning near field optical microscopy are studied in this module. Also, the general setup of transmission mode SNOM is discussed. The classical optical microscopy resolution limit. This was formulated by Abt in 1873 and it has been an insurmountable hurdle restricting features detectable by optical microscopy to about one half the wavelength of light. Non-optical methods such as electron microscopy and tunneling microscopy have been invaluable in our understanding of the world on a smaller scale. But these suffer from their own limitations and can't benefit from the centuries of studies using light. In 1928, as a series of discussions with Albert Einstein, Edward Strange proposed a series of discussions with Albert Einstein, scientist Edward Strange proposed an optical microscope design that could overcome the Abt barrier. His remarkable instrument included a glass needle probe with a sub-wavelength aperture, evaporated coatings to confine the light field, piezoelectric motion control, and a raster scan images. Due to the limited instrumental techniques of his time, Sen's vision would have to wait for over 50 years. With techniques developed for the scanning tunneling microscope, Dieter Pohl et al. Developed the scanning near field optical microscope, which is also known as SNOM or NSOM, in 1984, whose resolution goes well beyond the Abt barrier. Present-day SNOM design closely resemble Sen's original idea, as hundreds of research groups throughout the world uses SNOM's combination of optical characterization with nanometer spatial resolution to investigate a wide range of surfaces. The versatility of SNOM techniques is impressive. However, applications have been challenging owing to the difficulties in understanding the acquired images. Notably, SNOM signals are significantly influenced not only by the optical parameters and structure of the sample but also on the detection conditions. Some modeling work has been done in understanding how SNOM contrast depends on wavelength. In standard SNOM, light of only one wavelength is used to image the sample surface. Although this technique has proved successful, it is lacking in two areas. First, the identification of scanning artifacts, and secondly, the resolution of different chemical species in the sample. We next discuss about the evanescent waves and optical resolution. In the case of propagation in a vacuum, we know mu is equal to mu naught, epsilon is equal to epsilon naught, and conductivity sigma is equal to 0. Or in a dielectric, also we know sigma is equal to 0. So Maxwell's equations describes plane harmonic waves by the equations E is equal to E naught into e raised to power iota k dot r minus omega t, and H is equal to H naught into e raised to power iota k dot r minus omega t, which is traveling in direction k with frequency omega, and speed v is equal to 1 divided by square root of mu epsilon. Consider such a wave which is incident upon an interface as shown in figure 1. In figure 1, we can see that there is a linearly polarized electric field wave E which is incident upon an interface in the xy plane as a transverse electric mode. Let us examine the electric field where the magnetic field is completely analogous. The reflected and transmitted waves can be expressed as ER is equal to E naught R e raised to power iota KRR minus omega RT, and ET is equal to E naught T into e raised to power iota KTR minus omega TT respectively. The boundary conditions at the interface gives us the law of reflection, where theta is equal to theta r, and the Snell's law of refraction, where n sin theta is equal to nt sin theta t. When cos theta t is equal to square root of 1 minus sin square theta t, which equals square root of 1 minus sin square theta by n square, becomes purely imaginary for angles greater than the critical angle, that is sin theta greater than n. In that case, total internal reflection occurs. Now, writing cos theta t equals iota into square root of sin square theta by n square minus 1, we obtain vector kt dot vector r is equal to kt sin theta t cos theta t 0 dot product with x, y 0. This equals kt into x sin theta by n plus iota times kt into y into square root of sin square theta by n square minus 1. Now defining the real positive number alpha equals kt into square root of sin square theta by n square, the transmitted wave may be expressed as Et equals E naught t into e raised to power minus omega t into e raised to power iota xkt sin theta by n into e raised to power minus alpha y. This is an example of an evanescent wave characterized by an exponentially decaying amplitude, that is, it is equal to er whole square, which is proportional to e raised to power minus 2 alpha y. The number alpha is related to the skin depth by delta equals 1 divided by alpha. This equals lambda divided by 2 pi into square root of sin square theta by n square minus 1. A typical value of the skin depth in the visible spectrum is 10 nanometers, which can be seen in the figure 2 as shown. Whereas plane waves, they dominate in the far field or where the evanescent waves play a crucial role in near field optics as the principal optical imaging mechanism. The term near field, used in this context, refers to the region where the evanescent waves still contribute and should not be confused with the classical or Fresnel near field, which is at least a wavelength further away. Far field effects such as diffraction play a dominant role in classical optical microscopy. Consider a light source which is placed behind a circular aperture of diameter d. The image observed at a large distance away, that is, at a spacing z greater than d squared by lambda, that is, much greater than both the aperture and the wavelength, is the familiar Bessel function diffraction pattern. As shown in figure 3, the figure 3a shows electric field created by far field or Fraunhofer diffraction by a circular aperture of diameter d, whereas the figure 3b shows the airy rings, which depicts intensity distribution of diffraction pattern varying as 2 times J1 into K into d by 2 sine phi divided by K into d by 2 sine phi overall whole square, where phi is the angle from the center of the aperture to a point on the pattern, and K is the wave number, and J1 of rho is the Bessel function of the first kind. In regard to the ultimate resolution of a microscope, consider two such patterns which are placed close together. The Rayleigh criteria for just resolvable images requires that the center of one pattern's airy disk, that is the bright central disk, lie no closer than the first minimum of the second pattern. Under incoherent illumination, this corresponds to an angular separation of theta min equals 1.22 into lambda divided by capital D. If one considers a geometry where a lens is used instead of an aperture as shown before, the fundamental or diffraction limited resolution limit, that is, the Abbe barrier, is found to be delta x min equals 1.22 into lambda divided by 2n sine phi, where n is the index of refraction of the medium between object and the lens. This expression is often written in terms of the numerical aperture of the lens, that is, delta x min equals 0.61 lambda divided by the numerical aperture. Using Fourier optics, we may show that this is not a fundamental limit. Rather, it arises due to the imaging element, that is, the lens, which is many wavelengths away from the sample. High spatial frequency components decay rapidly with distance from the object, and so in the far field regime, only low frequency components remain, which limits the resolution. In classical optical microscopy, resolution even slightly beyond the wavelength of light is difficult to achieve, and it requires great effort. The limitation of the resolution to hundreds of nanometers was the driving force behind the move to the near field and the development of SNOM. Under a completely general formalism, we may express any two-dimensional electromagnetic field distribution, that is E, which is a function of kx, ky, kz to be equal to E1 e raised to power iota kz into z plus E2 into e raised to power minus iota kz into z as an infinite number of incoming and outgoing plane and evanescent waves. The evolution of the Fourier components E1 and E2 determines the field distribution during propagation in the reference plane where z is equal to constant. Using a suitable source or detector, we may create or probe evanescent modes and are thus no longer limited by the constraints of propagating far field waves. The essence of near field microscopy is to create such sub-wavelength probes, forget the effects of diffraction, and investigate high spatial frequency modes of the sample surface. That resolution is limited to the dimensions of the detector may also be thought of in terms of signal processing. Assume a sample consisting of co-sinusoidally varying features of spatial frequency alpha, that is, g of x is equal to 1 plus cos of 2 pi into alpha x. We may model the near field probe as a rectangular detector of aperture d and response function s. Assume a relative motion between the detector and the sample with velocity v. This represents the scanning process and converts spatial frequencies to temporal ones. In particular, f is equal to alpha times v, and the detector signal is given by h of t is equal to s into the integral going from minus infinity to infinity g of x into rect function x by d dx. This is equal to s into the integral going from minus d by 2 to plus d by 2, the under the integral sign 1 plus real part of e raised to power 2 pi t ft minus alpha x dx. This is equal to st plus s by pi alpha into sine of pi alpha d into cos of 2 pi ft. It is clear that to maximize the detector signal at high spatial frequencies, we must have d equals 1 divided by 2 alpha, and this represents the minimum detectable resolution. Note that this assumes the detector is close enough, that is, the near field to the sample, to probe the high spatial frequencies. The limiting resolution of a SONM is then the greater of the sample features or the probe size, neither of which is restricted by considerations of wavelength. As can be seen in the figure, there is a rectangular detector of aperture D which scans over the high frequency features g of x equals 1 plus cos of 2 pi alpha x of the sample at a velocity v. Here, the minimum detectable resolution occurs for d equals 1 divided by 2 alpha. Let us next study the various modes of operation. We will first discuss about the aperture and apertureless operation. There exists SNOM which can be operated in so-called aperture mode and SNOM for operation in a non-aperture mode. As illustrated, the tips used in the apertureless mode are very sharp and they do not have a metal coating. Though the typical metal coated tip is shown in figure 5a and a sharp uncoated tip is shown in figure 5b. Though there are many issues which are associated with the aperture tips, that is, heating, artifacts, contrast, sensitivity, topology, and interference, amongst others. But still, aperture mode remains more popular. This is primarily because apertureless mode is even more complex to set up and operate and is not understood as well. There are five primary modes of aperture SNOM operation and four primary modes of apertureless SNOM operation. The major ones are illustrated in figure 6. We can see the aperture modes of operation in figure 6 where A shows the illumination, B shows the collection, C shows the illumination collection, D indicates reflection, and E gives the reflection collection. Figure 7 shows the apertureless modes of operation where A shows the photon tunneling by a sharp transparent tip, which is also known as PSTM. Figure B shows PSTM by sharp opaque tip on smooth surface. And figure 7C shows the scanning interferometric apertureless microscopy with double modulation. Some types of SNOM operation utilize a campanile probe which has a square pyramid shape with two facets coated with a metal. Such a probe has a high signal collection efficiency that is greater than 90% and no frequency cutoff. Another alternative is active tip schemes where the tip is functionalized with active light sources such as a fluorescent dye or even a light emitting diode that enables fluorescence excitation. Let us now discuss about the feedback mechanisms. Feedback mechanisms are usually used to achieve high resolution and artifact-free images, since the detector must be positioned within a few nanometers of the surfaces. Some of these mechanisms are: number 1, constant force feedback. This mode is very similar to the feedback mechanism used in atomic force microscopy, that is AFM. Experiments can be performed in contact, intermittent contact, and non-contact modes. First one is the shear force feedback. In this mode, a tuning fork is mounted alongside the tip and made to oscillate and at its resonance frequency. The amplitude is closely related to the tip's surface distance and is thus used as feedback mechanism. Contrast. It is possible to take advantage of the various contrast techniques that are available to optical microscopy through SNOM but with much higher resolution. By using the change in the polarization of light or the intensity of the light as a function of the incident wavelength, it is possible to make use of contrast enhancing techniques such as staining, fluorescence, phase contrast, and differential interference contrast. It is also possible to provide contrast using the change in refractive index, reflectivity, local stress, and magnetic properties, amongst others. Let us now discuss about the applications of scanning near-field optical microscopy. The most important application of scanning near-field optical microscopy is in the study of single molecules. Here, the single, usually fluorescence of a single molecule is detected. The dynamics of the molecules, the local environment of the molecules, the polarization dependence of emission, and thereby the orientation of the dipole moment of molecule, photobleaching, etc. have been investigated. We next study the general setup. A quasi-point-like source of light is brought into the near field of a thin sample. The light is then collected using a lens after propagating through the sample. The basic components of a transmission mode SNOM are shown in figure 8. We can see the schematic of the transmission mode SNOM, where one can easily infer that SNOM shares much of its design with other scanning probe microscopy members such as the atomic force microscope and the scanning tunneling microscope STM. The fiber tip is scanned over the sample while monitoring its interaction with the surface. By keeping this interaction constant, one attempts to maintain a constant tip sample distance. Laser light is coupled into the free end of the optical fiber after being attenuated by neutral density filters. Light emanating from the tip passes through the sample and is focused by a microscope objective through a small pinhole and onto a sensitive detector. Images are created by raster scanning in X and Y, maintaining a constant shear force and acquiring the intensity of transmitted light. A computer records the Z position of the sample and the transmitted light intensity as a function of position to generate the topography and optical images respectively. A removable mirror and an optical microscope are frequently used to align the optics before scanning begins. So students, let us now summarize what we have learned in this module. In this module, scanning near-field optical microscopy, that is SNOM, was described. Then, the evanescent waves were described and the optical resolution was discussed. The various modes of operation, feedback mechanisms, and contrast techniques of SNOM were studied. The general setup of transmission mode SNOM was discussed in this module. Thank you students for your attention.